Alright, so in this example we have this rather complicated little system shown below, and we're asked to find the equation of motion for the system in terms of the coordinate x and also to find the natural frequency of the system. So in this regard, as we do in most equation of motion problems, we're going to want to draw a free body diagram for each particle in the system. And in this case, this will be my particle A, and let me just see if I can draw down an angle just to make sure we keep them clear. This will be my particle A. And I'll also have my particle B, which I'll choose to draw down here. Now if we go ahead and start by drawing the forces on this particle A, we know first of all we'll have the weight force mg, and we'll have also a normal force normal to the incline n. And we can assume here that the surface is smooth. It's actually quite difficult to solve Vibes problems with friction on the surface. And we'll also then, of course, if x is positive, we'll have a tension force here, as well as a spring force pulling back of magnitude k times x. And we know this block is allowed to translate up the slope, and it will be given by mx double dot. Now if I draw a free body diagram also here for my block B, then I know I'm going to have in this case 2t pointing up, because we have two lengths of cable suspending this block. We'll have f of t pointing down, and we will also have the weight of this block, which is mg, pointing down. And we can go ahead and say that this block is moving slightly downward with some amount we'll call my double dot, where we use y to define the downward coordinate here. Now the only other thing that might be helpful at this juncture is to account for the angle theta. And so I'll simply note that the angle of inclination here internal to the system is the angle theta, because that's going to help me out in a minute. Now to do the kinetics, step 2 if you would of our 4-step program, what I'm going to do is I'm going to start by summing forces in the x direction on block A and set that equal to mx double dot. And of course I'm going to do this in a way that's positive up the slope using my x coordinate. And so if I do this, what am I going to get? Well, I'm going to get t minus kx minus mg times the sine of the angle theta is equal to m times x double dot. I'm going to then choose to summate my forces in the downward positive direction on block B and set that equal to my double dot. And if I do that, what I'm going to end up with here is that minus 2t plus f of t plus mg is going to equal m times y double dot. Now at this juncture, probably it would be nice to go ahead and eliminate t, and so if I do that I can note from, let's first of all call this equation 1 and equation 2, that equation 1 is going to give me that t is equal to mx double dot plus kx plus mg times the sine of the angle theta. So if I then take that and plug that into equation 2, I'm going to get that minus 2 mx double dot minus 2kx minus 2 mg times the sine of theta plus f of t plus mg is equal to m times y double dot. Now I don't have a satisfactory equation of motion yet because I still have two kinematic variables left in this system, and so I need to come up with a way to eliminate those. Because of the presence of the rope in this problem, the way I'm going to do that is through the rope length constraint. And so what I'm going to do here is let me sketch a quick sketch of my rope. I know it looks something like this. And so I'm going to do this by again summing up rope lengths. And so if I do that, I know this distance right here is some constant minus the displacement x. I know that rope gets shorter as x moves in a positive sense, and that's why I know it's a constant minus x. And I know the lengths of these rope segments are related by at least within a constant to y. And so this means that my rope length constraint is going to give me that some constant minus x plus 2 times y is equal to some other constant, which I'll call c2. Now I can go ahead and erase the c from this side and then simply get that that's equal to a constant. Now if I have that, I can take the second derivative of that and note that minus x double dot plus 2y double dot has to equal 0, which of course gives me that y double dot has to equal x double dot divided by 2. If I take that result and plug it back into the equation that I previously found, namely right here, what I'm going to end up with is the following. I'm going to have minus 2 times m times x double dot minus 2 times k times x minus 2 times mg sine theta plus f of t plus mg is equal to 1/2 mx double dot. To get the equation of motion now, I'm just going to put this into what we call standard form, which is we move all of the terms involving x on one side of the equation. So if I do that, I'll move the 2mx to the other side and end up with 5/2 mx double dot. I'll move the stiffness term over, so I'll have plus 2kx, and that's going to equal f of t plus mg minus 2 times mg times the sine of the angle theta. And that'll be the differential equation of motion for this system. And then the next thing I want to find is the natural frequency. And so to do that, what I'm going to do is I'm going to note that this is the effective stiffness of the system, which I'll call capital K. And this is the effective mass of the system that I'll call capital M. And I'm going to note here that the natural frequency is equal to the square root of capital K divided by capital M, the effective stiffness divided by the effective mass. So in this case, it's going to be the square root of 2K divided by 5/2 M, which is going to equal the square root of 4K over 5M. And that'll give me the natural frequency of this system. Best of luck as you work to reproduce this example.